Hey, Calc students, another FRQ from an old AP exam. This question is from the year 2012, and this is question number 5. So it's a non-calculator question, and if you look right at the top, you see a differential equation, so a good conclusion would be, well, this is probably a differential equation style. And it is. It's got a little bit of a curveball in here, but it's a good little question. So let's read and see what we're dealing with here. Well, it says the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Well, if you're not used to this lingo, or you haven't done this for a while, it was actually very common in algebra class, it's when something is proportional. When you have two items that are proportional, it's really no different than saying that you have a direct relation. If you think back to Algebra 1 when you had direct relations and inverse relations. So just so you don't get thrown by this in a question, I want to go over just what that would look like. So for example, if you heard in a sentence, if you said y is proportional to x. Y is proportional to x. There's two ways to look at that. You could say, well, y is proportional to x, so there's my proportion, and there would be some constant of proportionality, and I'll call that k. So k is a constant, not a variable. Or you could have looked at that and said, oh, well, that's the way to say a direct relationship. You could have said y is proportional to kx. Either one of those is fine. Well, let's look at what they say in the question. The question says the rate at which a baby bird gains weight. Well, the rate at which a baby bird gains weight is dB dt. That right there, remember, a derivative is an integral, a derivative is a instantaneous rate of change, differential equation. So this right here is representing the rate the baby bird's weight changes. So the rate that a baby bird gains weight, that's this thing, is proportional. Well, what they decided to do was use this example right here, and they said is equal to some constant. It's proportional to the difference between its adult weight and its current weight. Well, its adult weight is 100 grams, and its current weight is whatever its current weight is. It's B. So this is the rate the body weight is changing, is proportional to the difference of its adult weight and its current weight. Well, for this problem, the constant of proportionality is actually 1/5. So that's where that came from. The reason it's important to understand this lingo is sometimes you have to create the equation based on what's written. They don't give it to you. But this is actually just, you want to make sure you don't get thrown by a lingo or a notation issue here. So that's where this differential equation came from. And so it also tells you at t equals 0, when the bird is first weighed, it's 20 grams. So at t is equal to 0, we are at 20 grams. And it looks like our time here is in days. So on day 1, when the little bird is born or hatches out of its egg, it is 20 grams. And when it's an adult, it's going to weigh 100. Okay? And so the rate that its weight is changing is proportional to the difference in its adult weight and its birth weight, or hatched weight, and 1/5 happens to be the constant proportionality. So that's what this differential equation means that we're given. Okay, so hopefully that makes sense. And now that we have this and this, let's see if we can attack part A of the question. So it says, and by the way here, we also could have written this as a b of 0 is equal to 20. That's just the function notation of that information. So it says, A, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your answer. Well, it's as simple as just substituting those values into this right here. So the rate its weight is changing is the bird gaining weight faster when it's 40 versus when it's 70? Well, we just have to substitute those values in here. So I want to figure out what is dB dt. And if you ever see this notation sometimes gets used. We're going to say, let's do this when the body weight, what's our first one here? When it's 40. So when the body weight equals 40, well, that's going to equal 1/5 times 100 minus 40. Well, 100 minus 40 is 60. 60 over 5 is going to equal 12. Okay? Now let's compare it to, what is it when it is The second one, it said when it's 40 or when it's 70. Okay, well that's going to be 1/5 times 100 minus 70, which would be 30, and that would wind up being 6. So the rate the bird is gaining weight, it's gaining, looks like here, 12 grams per day when it weighs 40, and only 6 grams per day at when it weighs 70. So when it's a little lighter, its actual rate that it's gaining weight is faster. And so we would just draw a conclusion, and we would say the bird is gaining weight faster when it weighs, and again, when it weighs 40 is when it's faster. The bird is gaining weight faster when it weighs 40 grams than when it weighs 70 grams. So these were grams, not days. When it was weighing 40 grams, it was increasing at a rate of 12 grams per day. When it was a little heavier, it was still gaining, but not quite as fast. So the bird's gaining weight faster when the bird weighs 40 grams than when it weighs 70, because 12 is greater than 6. Okay? And that's A. Now let's look at part B. B says find d squared b over dt squared, which is another way of saying find the second derivative in terms of b. So let's do that first. There's an application question to it as well. So let's just find that first, and let's see if we can fit that in right here. And so I'm going to say, well, we better just put down the original first. So db dt is equal to 1/5 times 100 minus b. Okay. Now, this is not difficult over here, but students still struggle with this, so I'm just going to write this a little bit different. I'm just going to say, okay, all I'm doing here is distributing the 1/5 in there first. So if I distribute 1/5 in there, this is going to equal 20 minus 1/5 b. If I don't do that, for whatever reason, this throws students like you have to do the product rule, and they make this derivative way too hard. But this is what it would also be if you distribute the 1/5. Well, what the question is saying is find the second derivative with respect to t, so I'm taking d dt of this. Okay? So, I'm going to erase this other work here, get this out of the way. Okay? So, let's take the derivative of db dt. Well, that's where we're going to get our d squared b over dt squared. Okay? Now, the derivative of 20 is 0, so that's gone. The derivative of negative 1/5 b, well, that would be negative 1/5, but you got to be careful. Derivatives don't match, so I got to represent with the derivative of b with respect to t would be db dt. Okay? Well, db dt is this thing we started with up here. So now replace db dt with what it equals, that up there, and our final answer would be d squared b dt squared is equal to negative 1/5 times the original statement. So that's going to be negative 1/25 times 100 minus b. I'm actually going to return to the original one. It makes it easier. Okay, so there is my second derivative. Then the question says, use that to explain why the graph of b cannot resemble the graph they gave us. That's interesting. Well, let's look at the graph they gave us. It looks like the graph they gave us is increasing, and it's increasing the whole time. And it looks like we have a point of concavity. Now, what you should be thinking of when you see second derivative, that's a big hint that there's something to do with the concavity here, is what they want us to look at. So let's read the question again. There's a hint in here. It says, use the second derivative to explain why the graph of b isn't this one. Well, if this isn't right, it's got to be because there's something wrong with the concavity on this one that our second derivative test won't support. So that's a little bit, nuance there to see that. So let's go ahead and see what we would get if we took our second derivative and got our potential inflection points. Okay, we got our pips. So I'm going to take my second derivative here, and I'm going to say, okay, I'm going to set that equal to undefined and 0, and see if I have any pips in here. So when is it undefined? Never. When does this thing equal 0? It's pretty easy, actually. You can see right away. It would be 0 when b is equal to 100. Okay? Well, if b is equal to 100, we would have a potential inflection point there. Okay, so let's go ahead and test it. So if this is our b value here, I only have one inflection point, so it would be 0. And this is kind of weird. 0 to 100, because that's the heaviest the bird ever is. So let's pretend you didn't know that, and you just said, well, I'm just going to put a 100 right here, and I'm not even going to put a value here. Okay, I'm just going to leave it. And for the sake of the problem, if you want, put 1,000. But you'll see here in a second what the issue is. So let's go ahead and pick a number in the interval from 0 to 100. Any number in the interval 0 to 100, let's pick 50. If you put it in here, 100 minus 50 is positive. Positive times a negative is a negative. This would be negative and concave down. Pick any number more than 100. 100 minus that's going to be a negative number. Negative times a negative is positive, and you would be concave up. So it looks like we have an inflection point at 100. Well, here's where you got to be careful. This is the b value. And again, we're so used to looking at things horizontally. Here's what was a little bit mean about this. This tells me I do have an inflection point, but it's when b is 100. So let's look at this graph. B is the vertical axis. So that's telling me I have an inflection point up here. But actually 100 is a limiting value. And if I did have an inflection point, it looks like it would be somewhere like right there. It looks like my concavity changes, I don't know, ballpark it somewhere around 60 maybe. And our inflection point wouldn't occur until after 100. This doesn't make, these don't match. So explain why the graph of b cannot resemble the graph following here. I would say the graph has an inflection point between 20 and 100, and there is no inflection point between 20 and 100. So I would say it this way. The graph shows, actually I'm going to say a change in concavity. A change in concavity somewhere when b is greater than 20 but less than 100. But the second derivative, d squared b over dt squared, in that entire interval is negative the entire time. So is less than 0 for all b less than 100 greater than 20. Okay? So in order to have a change in concavity in the interval, this would have to equal 0. So the graph shows a change in concavity in the interval, but this is negative for all of that time. That implies that it's never 0. If you wanted to, or you could say, or db dt, sorry, d squared b over dt squared does not equal 0 in the interval 20 less than t less than 100. And the graph shows there would have to be one. Okay? That's what you're addressing with that part of the question. Okay? So 2 points for this first part here. Just which one's faster. And so the reason a student would miss this one is that you didn't quite understand what I had said originally about what does this actually mean. This just represents the rate your weight's changing. So they give you 2 values and compare them. And then the next one is just, can you take a derivative and put the value in? Even if you missed your explanation, you could have got your point for your second derivative. Okay? So there's 2, 2, and now we're down to the last part here. And the last part says, use separation of variables to find y equals b of t, or basically just solve the differential. Okay, so if you're good at solving differential equations, this is where 5 points are, and let's see what we can do here. So the equation is db dt is equal to 1/5 100 minus b. So can you solve that equation? Step 1, let's bring the 100 minus b over here. So this is going to be db over 100 minus b is equal to 1/5 dt. Okay? Separated my variables. Step 2, I'm going to integrate. So I'm going to integrate both sides, and what I'm going to do here, I'm going to integrate this, I'm going to make this 1 over 100 minus b db, and that's equal to the integral of 1/5 dt. Okay, separate your variables, integrate both sides. This side of the integral, the right side's very easy. That's just going to generate a 1/5 t plus c. Done. This side, for some of you, this is a one-stepper, but you have to be careful. This denominator, technically we would have a little u substitution over here that I'm going to do in case you need to see that. And I'm going to say, well, I'm going to let u equal 100 minus b. I'll show you what happens here. I replace this with u, okay? And when over here I go to take my du, I get a negative db. And that's what can burn you. The negative got generated. So it's a negative du is equal to db. So I replace this with 1 over u. I replace that with u. And I'm going to replace db with a negative du. So I'm going to put the du there and I'm going to move the negative out front. Okay. So we should all know the integral of 1 over u is the natural log of u. So I'm going to make this negative natural log of the absolute value of u, but I'm going to put u back in, which was 100 minus b. And that is equal to 1/5 t plus c. Okay. Now it's at this point, I would go ahead and solve for c. And if you remember in the question, they tell you b of 0 is equal to 20. So I'm going to highlight that right here. This was given. B of 0 was equal to 20. Okay, given. So that just means time is 0, and that b is equal to 20. I'm going to substitute those in there. So I'm going to say negative natural log of 100 minus 20 is equal to 1/5 times 0 plus c. Simplify that down, I get negative the natural log of 80 is equal to c. And I'm going to take that value and sub it back in right there. So now my equation is negative the natural log, absolute value of 80 is 80, so I can just leave it. Negative the natural log, or I'm sorry, I'm ahead of myself here. Back to a 100 minus b is equal to 1/5 t, and now instead of plus c, I'm going to put minus the natural log of 80. Okay. Now it's time to solve for b. b right now is trapped inside a logarithm, so it's kind of some old pre-calc skills here. So normally we'd rewrite this as an exponential, but I want to get rid of this negative because that creates real headaches when you go to convert. So I'm just going to multiply everything by negative. So this is going to be the natural log of 100 minus b is equal to now negative 1/5 t plus the natural log of 80. Now I'm going to Roman numeral 9 it, or just bring this down. Remember, this is log base e, so I'm going to make an e here. And so, just so everybody knows, this is actually log base e. So I'm bringing e down, and I'm bringing this to be the exponent over here. Okay, I want to make that too long, or I don't have enough room. So this exponent now is negative 1/5 t plus the natural log of 80. And then this is going to go to the other side of the equal sign, is equal to 100 minus b. Now, I'm going to take off my absolute value, and here is why. In the question, if you'll notice here, the adult weight is 100. B, it never gets there. B is always less than 100, so I don't need my absolute value anymore. So I'm just going to take it off. It's not necessary. So now I have a little cleanup here to do. If you have a sum in your exponent, if you recall, I'm going to write this and then erase it. If you have x squared times x to the 5th, you add your exponents. And you say, oh, well, that's x to the 2 plus 5, and that's equal to x to the 7th. You've been doing that since pre-algebra. Well, when you get these exponents right here, we're just having you undo it like this to help clean that up. So, what we have here, I'm going to break this up into two separate pieces here. So I have e to the negative 1/5 t times e to the natural log of 80, and that equals 100 minus b. And then this has a property that hopefully you remember. If I had 2 and my exponent was log base 2 of x plus 3. We'll just say it was that. If you have an exponential statement, and the exponent is a logarithm, and the base of the logarithm matches the base of the exponential, they have a property of what most students say kind of cancel each other out or undo each other. So it just equals the argument. So it's just going to equal x plus 3. Well, this right here, e, the exponent is a logarithm with a base of e. So if you want to, you could think of it as canceling each other out. It's not really the exact way to say that, but it works. So this actually winds up just equaling 80. So I have 80 times e to the negative 1/5 t, and that's equal to my 100 minus b. So now all I'm going to do is going to bring the b over, bring those over, and clean it up a little bit, and I get b is equal to 100 minus 80 e to the negative 1/5 t. Okay, and then just to make it a function, I'm going to replace b with b of t, which is completely fine to do. And this is 100 minus 80 e to the negative 1/5 t. And that is the solution to this differential equation. That's where 5 points are. So this comes up a lot. There was no slope field on this one. But they decided to go with the second derivative question. So oftentimes the differential equations only have 3 parts because so often you have to solve a differential. And this differential equation wound up being a natural logarithm, or the actual solution was an exponential, but you transition through here a natural logarithm before you undo it. So first one, compare your rate. Second one, second derivative, and third one, solve this. Okay, so 2, 2, and 5. So there they are. That is 2012, question number 5, differential equation. Thanks for watching. We will see you next time.